Hi, my name is Ruth. I'm a PhD student at the University of York, studying how quantum entanglement can be used in a type of imaging called PET imaging. PET stands for positron emission tomography. It's a technique doctors use to image metabolic processes inside of the body, so it can be used to find cancerous tumours or to monitor brain activity. PET works by injecting a radiotracer into the body. This is commonly an isotope of fluorine attached to some kind of sugar. It travels around the body and gets absorbed into the tissue, accumulating in areas with particularly high metabolic processes. In other words, these are the parts of the body where there's a lot going on. So, for example, cancerous tumours. The radioactive atom then decays, producing a positron, which is the antiparticle of an electron. The positron will travel a couple of millimetres before annihilating with a nearby electron. The annihilation process produces two photons, which will always travel in opposite directions. These photons are detected by placing the patient inside a big ring of detectors. When we get two photon hits at the same time, we assume they came from the same event. We can then draw a line between the two hits, and we know that somewhere along this line is where the decay took place. We call this line a line of response. When enough of these lines have been collected, we can start to reconstruct an image of what's going on inside the body. Now, this is the ideal scenario. When the photons are detected cleanly like this, we call it a true event. The photons exit the body, interact with nothing, and then are immediately detected inside the scanner. What can actually happen is that one of the photons scatters and changes direction before it's detected. Photons can scatter in the patient, in the air, on the table, even in the detector itself. And when this happens, the line of response between the two hits is now offset from where the decay actually took place. The other issue that can occur is random coincidence. If two decays happen at almost exactly the same time, it's possible you'll detect one photon from one decay, one from the other, and then when you draw a line between your two photons, it's again pointing to the wrong location. These incorrect lines of response create noise and artifacts in our final images. Unfortunately, for a full-body PET scan, 30 to 50% of all the events we detect can be these scattered events, and that is a huge fraction. So as a result, PET scans tend to be noisy with bad spatial resolution. It's hard to see a lot of detail. Hospitals often try and correct for this by combining PET scans with other types of scans, like CT or MRI. These scans produce structural images of the body, which highlight bones and particularly dense areas. It just happens that these areas are those most likely to scatter photons, so we can then use these images to correct our PET scans. It works very effectively, but it takes a long time and may require exposing the patient to even more radiation. Here's where our research comes in. Our idea is to use quantum entanglement to remove these unwanted noisy events. Remember that the two PET photons are produced in the same event, when the positron and the electron annihilate with each other. So this means that they are quantum entangled. Anything that happens to one of my photons is going to instantly affect the properties of the other. Einstein called this spooky action at a distance. But we know that if one of the photons scatters, then entanglement between the two photons is destroyed. Also, if the two photons didn't originate from the same annihilation, so are from a random coincidence, then they would never have been entangled to begin with. What we need is a method to determine when we detect two photons, whether or not they're still entangled. If they are, it's likely to be a true event and we can keep it. If not, it's more likely to be scattered or random and we can throw it away. So, how do you measure entanglement? Our method looks at the way the photons behave when they hit the detector. When each photon hits the detector, it's quite likely to scatter at some angle. Let's call it phi. We're interested in the difference between the angles for the two photons. Let's call that delta phi. If the photons are entangled, delta phi looks like a cosine function, which means it's much more likely the photons scatter at right angles to each other than in the same direction. But if the photons are not entangled, then there's no relationship at all between the angles. The photons are equally likely to scatter at any angle, so delta phi is flat. So we should be able to use this information to work out which of the detected photons we should use for our image. So first of all, we're going to need a PET scan. We don't have a PET scan of our own to play with, but fortunately we can run a computer simulation of a scan. In our simulation, we build a large ring of detectors and place a phantom inside. A phantom is an object designed to mimic a real patient. So in our case, we used a phantom mouse. It's basically a little cylinder of plastic, and it contains 5 rods running through the middle. These rods contain a mixture of water and radioactive source. It's these rods that we're trying to image, so think of them like a cancerous tumour in a patient. Our program then makes a bunch of simulated decay events. Some of them might scatter, some of them don't. Our simulated detectors then look for pairs of photons arriving at the same time. First thing to do is find delta phi, the difference between the angles for all the photon pairs we detect. And as expected, this has a nice cosine shape. We can then reconstruct an image. For this first image, we're only going to use events with delta phi around 0. So these are the events we think are least likely to be entangled, so most likely to be scattered or random. So if we only use these photons, we can expect the image to look pretty bad. You can see 5 bright circles where the radioactive sources are, but the image is blurred and noisy. Now, if we reconstruct the same image, but use events with a slightly higher delta phi, then we expect a higher fraction of good events. And indeed, the image is a bit clearer. We can do this again for different delta phi sections, all the way up to 90 degrees. These are the events we think are most likely to still be entangled. And indeed, the image gets much clearer with better contrast and less noise. Using quantum entanglement information in this way, we can separate out the true events from the scattered events, the image from the noise, hopefully leading to better quality scans and more diagnostic success.